to be going over Lab 1, charged tapes and particles. My name is Brian McLeod. The purpose of our lab is to see how charged tapes interact and calculate the excessive charge on each tape. The physics ideas we will be using is that like charges repel, but opposite charges attract. The suspended tape floats because the electrical force is equal to gravitational force. Of course, Coulomb's law explains that the electrical force between the two charges. Models, a tape is modeled as a point charge, and the tape will also be modeled as a line charge distribution. Main results, the charge on each tape was calculated to be around 10 e to the negative 8 coulombs, with the line charge modeling being closer to reality. So the fundamental principles and models. So the electrical force, the tape experience an electrical force between each other because they are charged. We charge them with wool. Uh, they will they were repelled because they share similar types of charges, negative charges. Coulomb's law, where Fe equals K, which is Coulomb's constant, the charge of one particle, charge of the other particle divided by the distance squared. Gravitational force, although the tape is floating, it still experiences gravitational pull downwards towards the Earth. So we model this as Fg is equal to mg, so mass times gravity. If the tape was floating, this means that there must be an equilibrium of forces acting on the tape. So we know that F net must equal zero. So by that assumption, we can say that the force of the electrical charges must be equal to gravity. The repulsion of the forces must equal the gravity. This will let us estimate the tape's charge. So initial conditions in our experiment, we took a tape measuring about 0.2 meters, and the mass was estimated to be around 2 e to the negative 4 kilograms. A separation distance was about 0.021 meters. So the system is our top tape. The surroundings are the bottom table plus the Earth. The model setup, both tapes have the same sign of charges. They've both been charged to be negative. Tape charge was treated in two ways. Point charge model charged at the center of the tape, and the line charge model charged evenly distributed across the tape. So experimental observations. The system, tape B, and surroundings, tape A. Observations. Tape B was suspended above the table at approximately 0.025 meters. The force on tape B. Electrical forces acting upwards by repulsion with tape A. Gravitational forces acting downwards by the Earth. Key ideas. As tape B was suspended at constant velocity, the forces were in equilibrium. Again, the forces of repulsion must equal the forces of gravity to have a constant tape that's floating. Gravitational forces. So we can calculate our gravitational forces by multiplying our estimated mass by the estimated acceleration due to gravity, which is 9.8 meters a second, and we get approximately 1.96 e to the negative 3 newtons. The electrical force while floating. Since tape B is not accelerating, keyword not accelerating, they must be equal. Since it's in a constant hovering state, it must be equal to our estimated force of gravity. So charges on the tape. We can get our charge on the tape by plugging in our known variables. And so we get Q, which is coulombs, uh, the charge by plugging in our known constant, which is Coulomb's constant, plugging in the distance between the two tapes, and then also plugging in, um, you rearrange it and then you rearrange it and then you plug in coulombs on the bottom are constant, the force that we calculated, which is 1.9 e to the negative third, and then the distance between the two forces. If you rearrange it, you can find the charge Q of our tape. So essentially, we get our Q as being approximately 1.17 e to the negative 8 coulombs. Excessive electrons, multiple numbers of electrons. Uh, so we get Q divided by E, E being the charge, the charge that negative particles are, which is approximately 1.6 e to the negative 19. So we get 7.3 e to the 10 electrons, extra electrons, I guess. Goal. So our computational model goal was to model two charged tapes using GlowScript and calculate the required charge in order for tape B to float. So the point charge model. Two tapes are considered to be point charged in the center. So we only focus on one part. We focus on the center. The electrical force is acting upwards while the gravitational force acts downwards. As you can tell, although the yellow arrow is not really, you can't really see the arrow where it's pointing, but it's pointing downwards. But you also have a counteraction force occurring, which is that green. It's the one repulsing the top. Key outputs. Charges on the tape are equal to 1.17 e to the negative 8 coulombs. Electron loss is 7.29 e to the 10 electrons. Electron force on tape B is 1.96 e to the negative 3 newtons. So assumptions and errors. Tape B is not accelerating, so we can assume that the force of the electrons must equal the force of gravity. Tape A and B have equal net charges. We can assume that. Charges are considered at the midpoint of the tape, and the line charge approximation charge distribution was uniform along the tape, although in reality there might have been some uneven distribution of the electrical charges. Uniform charge distribution cannot be guaranteed. Tape may have lost some charge due to friction, difficulties in measuring distance between the tapes, inappropriate point charge assumptions. What if electrons and protons had reverse charges? The observation would be unchanged since all charges would be switched simultaneously. Two U-shaped tapes would also repel one another. A pin with a charge and a tape would still attract. All that would change was the labeling them of as being positive and negative. Why are point charges and line charge models different? Point charge models, all charges are located at the center of the tape, while our line charge models are distributed evenly throughout the length of the tape, making it more accurate since there are many charge bits at a diagonal distance. And that will be everything today.